Hello everyone, welcome to Rasayan Academy guys, and we are continuing with our name reaction series, and today we are going to talk about two very important name reactions, and those are reaction number 55 Woodward Cis Dihydroxylation and reaction number 56 Prevost trans dihydroxylation. Okay, so these two reactions are very similar and that's why we are studying them together. Okay, so before moving onwards, let me ask you to subscribe and like the channel if you already haven't. And yeah, let's start the mechanism. So first one is Woodward Cis dihydroxylation, and it's a very simple mechanism because if you're starting with an alkene like this, okay, let's say this is your tetra substituted alkene. So if you start with this alkene, and in the first step, if you provide the iodine, silver acetate, and in the second step, water as well as acid, so acidic workup. So you are going to get the cis diols. So this is a stereo specific reaction. Okay, take care of that. It's a stereo specific reaction. So also if you want to remember this, you can remember WC, that is World Cup, or you can remember water in cup. Because why? Because Woodward requires water and it gives you cis dihydroxylation. Okay, so Woodward cis dihydroxylation requires water and give you cis diol product. Okay, so first thing, let's draw the mechanism of what is happening. It's a very simple reaction. In the first step you have iodine, and what do you expect? That an iodine, when it reacts with an alkene, what do you expect guys? You are going to expect the iodonium ion formation in this way. All right, so this is your iodonium ion formation like this. Now if you want to be specific about the stereochemistry, we can actually write it like this. We can write the iodonium below in this way. Okay, now what is going to happen next? The silver took the I minus and it gave you a precipitate of silver iodide. And who is free now? The acetate is free. Free to attack. At one of these positions, SN to attack it will be. So normally there will be inversion. The iodine and the acetate are on the opposite sides. So there will be an inversion. Okay, so when the iodonium ion is forming below, the acetate has to attack from the opposite side. This will be an SN2 reaction, iodonium ion ring opening. And the next important step is NGP. So NGP is going on. What is NGP? Neighboring group participation. And because of the neighboring group participation of the acetate, I minus will also leave. So what just happened? Above the plane, there was an acetate. So acetate attacked this carbon once again above the plane. Okay, this is what you are going to get. All right, there will be a positive charge on the oxygen. A very simple reaction. Let's continue over here. So guys, Woodward cis dihydroxylation, the intermediate we have got already, that there will be a acetate who is doing the NGP, and this is what you result into. Now since there is water in this reaction, okay, there is water, so water is going to attack over this carbon, the bond is going to open up like this. If it happens, you are going to get oxygen, a carbon, one methyl. Since the water has attacked, the bond is going to open up from this side, so it will be um like this. There's an oxygen and there is only one single bond with the oxygen now, and there is OH. I am just removing the extra proton of the water. I'm directly writing it like this. Okay, now in the next step, you can expect to form an oxonium ion either by this oxygen or by the ring oxygen. Okay, whichever of them can form a oxonium ion, and the other one is going to leave like this. So you see, Yes, so there is now O minus, and since there is acid in the medium, it's not going to remain as O minus as it is, it forms, it will be taking away a proton. So this is partial hydrolysis that we have done. Now following the same mechanism, you will know that once again one more water molecule will attack over this carbon and automatically it's going to leave from here. So who is leaving, guys? Acetic acid is leaving CH3 COOH. It is leaving and you are getting the cis diol. So what is the what are the characteristics of Woodward cis dihydroxylation? First thing first, you are going to get the cis diol product. Second thing, you have to take care of water. Whenever you are spotting the reagents of Woodward cis dihydroxylation, it will be iodine, silver acetate. In the next step, you will have water, which is in the presence of dilute acid. Okay, so this is what you have to remember, a very simple reaction. Now let's look at an example. So let's say you have a molecule over here like this. Here you will see you have three double bonds. Now which double bond is going to be attacked? That is the question. If you want, you can try this out by yourself and stop the video. So let's say that you know these two are in conjugation with the uh, carbonyl. What does that mean? That means in a resonating structure, you must get something like this. Alright, that means you will have a positive charge over here onto this carbon if we do the resonance, right? That means, guys, that iodine, the first step of this reaction is electrophilic attack on the iodine. Who can do that? An electron rich alkene can do that. So this alkene is the only one which is isolated and it is electron rich. So we are kind of writing the intermediate from the isolated one because we want more electron rich alkene. Okay, there's a methyl, there's a hydrogen above, one more ring junction, hydrogen below and methyl above. Okay, so yes, one more important thing to consider, since the methyl is above, this methyl is above, where are you going to form the iodide? You will form it below the plane in this case. All right, and then where is the acetate going to attack? Definitely SN2. So the acetate could attack over here or it could attack over here as well. But ultimately, after the NGP step, when the iodine is completely removed, I am directly writing because it's a very simple mechanism. So I'm directly writing that your acetate will be attacking from above, right? And also it will be giving NGP from above. So this is what you have, and the rest of the molecule remains the same. Okay, right. Now what's going to happen, guys? You look in the reagent combination, it's iodine, it's silver acetate, acetic acid, and there is water. So when there is water, it is the Woodward cis dihydroxylation. Here the water is going to attack the carbonyl carbon, and one by one it's going to release the oxygens. Okay, so when it releases the oxygens, you are going to have a OH over here and another OH over here as well. So doesn't it seem very difficult to get the diol on the same side as the methyl, where usually it won't be? Why? Because yes, it is the more hindered side. But since your iodonium ion has attacked from below and this is a follow-up SN2 reaction, this is possible. Two consecutive SN2 reactions are happening to give you the retention, okay, OH above the plane, like this. Alright guys, so here we are on the another reaction, that is your Prevost trans dihydroxylation. Now it's also a very simple reaction and also very similar. So yes, let's start talking about it. So in the Prevost reaction, you see it's a trans dihydroxylation, which means that there is only a little bit of a change. Now, what is the change? Here in the reagent side, you don't have water added in the reaction mixture. There is no water. Just take care of that. So in the Prevost dihydroxylation, there is no water. Just that simple. Okay. And what is happening? The oxygen is going to be connected like this. Once you are getting the diacetate or the dibenzoate, whichever salt you want to take, after that, when everything is done, now you do the hydrolysis to finally hydrolyze the acetate or the benzoate group into alcohols. Hence, you get the transdiol. So let's talk about the mechanism. I hope that you will be able to draw this by yourself because not much difference in the mechanism, right? So you see the double bond is once again going to attack the iodine, give you the iodonium ion. Very similar process. Here also you will have the iodonium ion. Very good. But what next? See, if you want to take the benzoate, it's okay. If you want to take the acetate, it's okay, because both of them will have the same functions. Okay, I'm taking the benzoate over here. It will do an SN2 attack on one of the sides, and the iodonium bond is going to open up. Now, till here, everything is similar, isn't it? All right, everything is similar as compared to the last one, Woodward reaction. Now, what happens is once the NGP happens, see, there is going to be NGP like this. All right, once again above. So, this is your intermediate through NGP. Let's take this into the next slide. Yes, this is what you have got, NGP intermediate of the benzoate, right? But since you don't have water here, so water is not going to attack this carbon and hydrolyze both of these bonds to give you alcohols. Rather, what will happen is another acetate ion is going to attack on any one of them, which is possible. Any one of them can open up, and rather, they are going to give you trans dibenzoate. Okay, so you are going to get trans dibenzoate instead. Now this is the major step over here. In the last Woodward cis dihydroxylation, you had water attacking over this carbon and cutting these bonds from here, so you get OH. But here you don't have water. That's why the O minus is going to, the acetate is going to attack at one of these sides, give you trans acetate or trans dibenzoate. All right, and after the whole reaction is done, after this step is done, finally you do the hydrolysis, and that will break down, that is going to break down the benzoate bonds. You know, you can show it up like this, right? So water is going to attack over here in the last step, and then this bond opens away. So the same happens in the other one, and you are going to get the alcohol trans to each other. Okay, so if you just remember one of these, let's say you remember Woodward dihydroxylation, which is cis dihydroxylation. It requires water, W for water, C for cis, W is Woodward, right? And also you will be able to remember the opposite, Prevost is trans dihydroxylation with no water. Okay, so let's try this out on this molecule which is given over here. A very simple example, guys. Now you see that this is polycyclic aromatic compound, but there one cycle is present which is not aromatic and looks like this is a isolated double bond. Okay, so onto this double bond, which is also electron rich. Why is it electron rich? Because it is in conjugation with the other pi bonds. So it is electron rich. And what is the combination? You see only silver acetate or benzoate, and you see iodine. So what will happen first? First of all, you are going to get the iodonium ion, and here there is no specific stereo for it because the whole molecule is planar, isn't it? So you need not take very much care of where the iodine is going to be, above or below. All right, all of these four rings are aromatic, so let's just write the rings, and then you can add the benzoate or the any other acid salt. Let's say we add benzoate. What are you going to get? You are going to get something like this, and the rest of the molecule. So your final answer should be, so see, there is no water as of now, but what you're going to do is, if in the options, if in the CSIR options it is mentioned that it is like this only, and if it is mentioned you are having the diacetate or the dibenzoate product, you are going to stop over there. But what we do is, usually we don't stop, and after the getting this, you are going to what yeah, after doing this, after getting the diacetate or the dibenzoate, you are going to do the hydrolysis. In this way, it will be OH and OH over here. All right, chalo. So yes, this is your Prevost trans dihydroxylation. Very simple. Now guys, we are going to use this same concept in a CSIR net PYQ, which we have got from 2017, June 2017, I guess. All right. Now the correct combination of reagent A and B to effect the following transformation are: you have Norbornene system. What happens in the process A and what happens in the process B? So in process A, you are able to see that you are getting the diol. Both of them will give you cis diol only. What is the difference though? Here you get the exodiol, that is on the less hindered side. Here you get the endodiol, the more hindered side. So how is it possible? How are we going to create two different diols? This is a very good question. Now in the first step, if you see, if you do the oxidation by catalytic osmium tetraoxide, which is called the Upjohn oxidation reaction, okay, or you do it by alkaline KMnO4, both of them will give you the same product. Let's say both of them are going to give you a tetra substituted, this kind of a intermediate. Now this intermediate on reaction with OH minus is finally going to give you the diol on the less hindered side. Why is that so, guys? Because you see, if the alkaline KMnO4 has to attack the alkene and has to react the alkene, it will do so from the less hindered side because it is itself a bulky molecule. MnO4 minus, it's a bulky ion, so it's going to do that from the less hindered side. It will give you the exo product. Okay, and the same thing will happen with the osmium tetraoxide. It is also bulky. Both of them will form the exo. So we can say A and 1 and 2 could be correct. All right, now we move onwards into the second part. In the part B, let's see what's going on. So in the part B, guys, what do we see is the OH, both of them are below the plane. How is that possible? Let's say, let's say in option number B, first of all, we are providing iodine. Okay, so if we provide iodine, it's going to react on the less hindered side, that is the exo. Exo is the less hindered side, right? So it will react on the exo, or I should actually, write it like this for a better imagination of stereochemistry in this way. ठीक है? तो ये iodonium ion is going to form on the exo side. Now where is the acetate going to attack? See, in the second step you have phenyl. Okay, you have silver benzoate. Then once again, so let's take the silver benzoate only, like this. So silver benzoate is attacking from below and it's going to open up the iodonium ion. And one by one, after doing the NGP, I'm directly writing the NGP step. One by one, after doing the NGP, the benzoate will be added below in this case. All right. So if it is added below, right, and after the hydrolysis, you require this kind of a this diol which is endo. That is only possible if you are doing the Woodward Cis Dihydroxylation. Why? Because it's a cis dihydroxylation, so you need Woodward. So the B process is going to have iodine, silver acetate, not aqueous NaOH. It will require iodine, silver acetate, water. And in the second step, it could be acetate to just, uh, remove the excess of acid or work up. But it's this combination that you require with water in the first step. That will be Woodward. The first conditions are that of Prevost. Prevost, as you have seen, will give you trans. All right, and what about the other ones, guys? You have OSO4. TMEDA is not required. You don't have a OH group or any polar group. Once again, upjohn oxidation in B. In B, you won't get the upjohn oxidation because the four-membered osmium ring is not going to form on the endo side. It is more hindered. Okay, so I just hope that you understood this reaction. Very simple. Option number A is going to be your simple KMNO4 oxidation. Second is your answer. All right, and the B is going to be Woodward cis dihydroxylation. All right, so more name reactions coming up just like these ones. And till then, guys, keep liking the videos and also please share it to your friends if you think that these are important and it might help them as well. So, yes, I'll see you very, very soon.